Hello everyone, this is Tunay, and I'm a mechanical engineering student. What if I told you that something you cannot see with your eyes can decide how safe a car is during a crash? We often think strength comes from thicker materials or stronger alloys. However, in materials engineering, strength can also come from something much smaller grain size. So today, I want to show you how the internal structure of metals, specifically grain size, plays a crucial role in strength and safety. Grain size is an invisible parameter, but it strongly controls how metals deform, absorb energy, and ultimately protect us in real applications. As you can see in the image, we observe a car from the outside, but a magnifying glass reveals what is happening inside the material. This visual represents a fundamental idea in materials science. Decisions made at the microscopic scale determine performance at the macroscopic scale. Strength is not only determined by chemistry or geometry. Grain size plays a critical role in mechanical behavior, especially in safety critical structures such as automotive components. Metals are made of atoms arranged in crystal structures. A grain is a region where atoms are arranged in the same crystal orientation. As shown in the schematic image, a metal is not a single continuous crystal, but a collection of many grains with different orientations. These grains form during solidification and fit together like a three-dimensional puzzle, creating the overall microstructure of the material. Grain boundaries are the interfaces between grains with different orientations. Inside each grain, atoms are arranged in a regular and repeating pattern. However, at grain boundaries, this atomic order is disrupted. You can think of grain boundaries as thin, irregular zones where atomic alignment changes direction. Although these regions are microscopic, they strongly affect mechanical behavior because they influence how defects and deformation mechanisms move through the material. Plastic deformation in metals occurs mainly through dislocation motion. Dislocations are line-like defects in the crystal lattice that form when metals are bent, stretched, or compressed during processes such as bending, rolling, or forming. When stress is applied, dislocations begin to move through the crystal lattice rather than breaking atomic bonds everywhere at once. As deformation continues, dislocations multiply and interact with each other. They can form complex, tangled networks inside the material, similar to a dense web of intertwined lines. This growing dislocation structure allows metals to deform plastically, making them tougher and more capable of absorbing energy without fracturing. Grain boundaries act as barriers to dislocation motion. As shown in the image, smaller grains create more grain boundaries within the same volume of material. When dislocations move and encounter these boundaries, their motion is slowed down or completely blocked. In materials with large grains, dislocations can travel long distance without interruptions. In contrast, fine-grained materials force dislocations to stop, pile up, and change direction frequently. This makes plastic deformation more difficult, increases yield strength, and improves resistance to permanent shape change. This is why reducing grain size leads to stronger material. This analogy helps visualize the concept. Dislocations are like people trying to move. In large grains, movement is similar to walking across an open field, free and uninterrupted. In small grains, movement resembles navigating a city full of walls and narrow streets, where progress is constantly blocked. The more obstacles present, the harder it becomes to move, which directly explains why fine-grained materials are stronger. The Hall-Patch relationship describes this effect quantitatively. As shown in the graph, yield strength increases as grain size decreases. The Hall-Patch equation directly links microstructure to mechanical strength by showing how grain boundaries resist dislocation motion. This relationship demonstrates that grain size is not a coincidence. It is an engineering parameter that can be designed and optimized to achieve specific strength and performance requirements. Grain size does not form randomly. Engineers actively control it through manufacturing process. As shown in the image, faster cooling during solidification increases the nucleation rate, meaning more grains form at the same time. When many grains form simultaneously, they grow less, resulting in a fine-grained structure. Plastic deformation followed by recrystallization further refines grain size. During recrystallization, new, small and strain-free grains replace the deformed structure. This is why grain size is not luck. It is a design choice achieved through thermomechanical processing. In manufacturing, fast cooling produces fine-grained microstructures that increases strength and toughness. Recrystallization eliminates work-hardened, highly dislocated regions and replaces them with new grains that restore ductility while maintaining strength. These principles are widely used in automotive and aerospace industries, where materials must be both strong and damage tolerant. Controlling grain size allows engineering to balance strength, ductility, and toughness for demanding applications. In automotive applications, fine-grained steels improve crash safety by absorbing more energy during deformation. In sheet metal forming, grain size influences surface quality and prevents deflects such as orange peel, which means a rough, uneven surface texture caused by coarse grains deforming non-uniformly during sheet metal forming. In aerospace components, controlling grain size improves fatigue resistance, durability, and long-term reliability under cyclic loading. Grain size is microscopic, but its effects are macroscopic. It links processing, structure, and properties. As we have seen in this video, invisible details at the microscopic scale determine how materials behave in real engineering systems. What we control under the microscopic ultimately makes structure stronger, tougher, and safer. So, the next time you see a metal structure, remember this. Its performance is not only determined by what you can see on the outside, but by the invisible details hidden inside the material. Thanks for watching my video.